Hi everyone. In this lecture, I will discuss the important concepts under the Bohr Atomic Model. This model shows that electrons travel in separate orbits around the nucleus. I will show here the quantization as a result of this atomic model with discrete energy levels. Let's start. This is the outline of this lecture. A little bit of history. Niels Bohr in 1913 studied the relationship between spectral wavelengths and energy levels. He also developed his model of the hydrogen atom, where he found an energy level in agreement with the values from the actual spectra. Next, we have here the discovery of the nucleus through Rutherford's scattering experiment. Rutherford suggested that electrons may be revolving in orbits about a certain nucleus, just like how the planets revolve around the sun. However, in the classical electromagnetic theory, an orbiting electron should continuously radiate electromagnetic waves, and it will spiral into the nucleus, as shown here in the drawing. Due to its varying radius, and the angular speed varies as well. Thus, classically, the frequency of the emitted radiation should also change continuously, as shown in the drawing. So we have different frequencies. In this classical scenario, we produce a continuous spectrum and not a line spectrum, which is what is actually observed experimentally. Bohr suggested that an electron can move around the nucleus in circular stable orbits without any photon emission, unlike what we have shown earlier for the classical electromagnetic theory. It will emit radiation or photon when a transition happens from one orbit to another. And this photon, the emitted photon, will have an energy based on the transition energy levels as shown in this equation. In addition, Bohr proposed that the magnitude of the electron's angular momentum, so note that angular momentum is just the rotation equivalent of linear momentum. This is quantized, where its magnitude is equal to the integer multiple of h, the Planck's constant, over 2 pi. The n here shows the permitted value of the orbit radius. So this is the n, and we can call it the principal quantum number for that specific orbit. We have this model of the hydrogen atom, wherein the proton is assumed to be stationary with mass capital M. Then we have this charge positive E. The electron revolves in a circular radius Rn and with speed Vn. As the electron orbits around the proton, it has a radially inward acceleration, as shown. So we have AC is equal to Vn squared over Rn. And using the second law of Newton, the magnitude of the inward force is expressed as this. Then this force F is similar with the electrical Coulomb attraction between these two charges. So we have the following. Using the second law, we have this final form of the Coulomb's law, and this force due to this centripetal acceleration. Okay, so using our quantized angular momentum, so this is our angular momentum, and the equation for the inward force of the electron, we can derive the orbit radii Rn and orbital speed Vn in the Bohr atomic model as follows. So we can get this R sub n, or the orbit radii, using equation number 2, this equation, and by getting Rn, so we have this expression. Let this be equation number 3. Then using equation 3, this one, and equation 1, we can get our Vn, the orbital speeds. Because doing some substitution, and we can isolate Vn, so we can have this final form of the orbital speed expression. So this is the orbital speed. So now we will get the expression for r sub n. We can find r sub n using this equation number 3, and equation number 4, which is our expression for our orbital speed. Thus, we can get this final expression for our orbit radii. The orbit radius is proportional to n squared, as shown, wherein n is our principal quantum number. We can get the smallest orbit radius by making n is equal to 1. So this is called the Bohr Reduce, which has this variable a naught. We can substitute the known constants to get the numerical value. And a naught, the Bohr Reduce, is equal to 5.29 times 10 to the negative 11 meters. So we know this constants. We can also rewrite the orbit radius in terms of the Bohr radius. So we have this final form of our orbit radii. Using the orbit radius and orbital speed equations, we can find the kinetic energy and potential energy when the electron is in the orbit with quantum number n. You can also have this form of your total energy. So just substitute your b sub n and r sub n here, and you can get these expressions. Note that the potential energy has a negative sign due to the fact that the potential is said to be zero when the electron is infinitely far from our nucleus. With our discussion of energy levels, we now have two expressions for our E sub n. The first equation, E sub n, refers to the measured spectrum of hydrogen, while the second one, the one that we were able to derive, this one, is from the Bohr atomic model. These equations can show us how to compute the Rydberg's constant value using the fundamental physical constants. So thus, this is the numerical value of our Rydberg's constant when we substitute those known constants. So we have r is approximately equal to 1.097 times 10 to the 7 per meter. So next we define ionization energy, which is just the energy we need to remove the electron completely in its orbital shell. For the case of the hydrogen atom, it is the transition from the ground level n is equal to 1 to an infinitely large orbit radius n is equal to infinity. This is the ionization energy, which is equal to E sub 1 or negative E sub 1, which has a numerical value of 13.60 electron volts. The value of the Rydberg constant R and the ionization energy for hydrogen predicted using Bohr's analysis are within 0.1% of the actual measured value. This agreement actually can be improved if we did not assume that the nucleus, which is the single proton, remains at rest. The proton and electron both moves in circular orbits as shown about their common center of mass with this x here. We have this Rn, Re, with respect to this orbiting electron. Using the reduced mass of this two-particle system with mass m1 equal to the mass of the electron and mass m2 equal to the mass of the proton, we have the reduced mass of proton-electron system equal to 0.9994 6 times the mass of your electron m sub e. Hi there, if you have learned something in this video and like my content, please consider subscribing my YouTube channel, JP Academia, and see you in the next video.